Welcome to this tutorial about GRAMM GRAL, a free software package including GRAMM, a prognostic mesoscale wind field model, GRAL, a Lagrangian dispersion model, and a graphical user interface. Hello, my name is Markus, and this is the first episode of the GRAL tutorial. I will create a simple project with one stack and compute the dispersion at flat terrain without buildings today. First of all, we have to create a project. Projects are organized as folders, therefore we create or open a project folder. In the first step, we have to define some basic model settings, for example the dispersion time, the particles per second, the surface roughness, and the latitude of the GRAL domain area. Because we will not take buildings into account, we don't have to set up these settings in this list box. Otherwise, GRAL would compute an internal GRAL flow field. As we will compute a stack without buildings and topography, a grid resolution of 20 meters should be small enough. I will compute two horizontal slices with a dimension of 3 meters at heights of 3 meters to collect the pollutants in an altitude between 1.5 and 4.5 meters above ground, and a second slice at 6 meters. Now let's go to the next step. It's recommended to define source groups before you digitize all sources. GRAL computes results for each source group, and therefore it's possible to use diurnal and seasonal emission rates for each source group. Let's define a source group called stack sources, click Add, and close this dialog. Now we can start the GIS interface. At the start we will need a georeferenced map. We can load a map using this button. Now we select a picture. This is a pure JPEG picture without georeference information. We can do this using 2 points or a scale and 1 reference point. Now in this picture we have 2 reference points at the edges of that bitmap, so we will use the option with 2 points. We can click to that button or use the menu entry for georeferencing. I select the points in the bitmap and define the real-world coordinates of the edges. You can take any picture here, but be aware that you define the coordinate system of your GIS window at this process. After that process, it's recommended to check the georeferencing using the length measurement tool. Now it's possible to define a point source, therefore I will use this tool. In the first step I have to define a name and digitize the position by clicking to the map. In the second step I will define the geometry and emission rate of this source. One can define a source group for each source in this dialog. Because we are using one source group only, we have nothing to do in this example. If I close the window by unselecting this checkbox, all data will be saved automatically. It's possible to check this using the option Selected Items. Last but not least, I have to define the GRAL domain area. That's the computation area of the model using this button. Well, that's all for a simple project. We can close the GIS window and go to the next step. In the domain tab, it's possible to check the geometry of the domain area and the number of cells inside the domain area. Because GRAL computes pure situations and stores the results of each situation and each source group, the emission variation is a part of the post-processing and can be changed after the computation if needed. Therefore, we don't change this value at the moment. The emission is 100% at all the time for our simulation. The annual emission rate for each source group can be checked using this button. At the Meteorology tab, we have to load meteor data from an observation station that represents the meteorology at the study area. It's possible to analyze the data here. We see the time span for this dataset, and it's possible to visualize the windrows, for example. Usually we will classify the meteorological data. Our MET file has a time span of 1 day only. So in this case we will not classify the data and compute each hour of our short meteorological time series. In episode 2 of this tutorial I describe how I generated this meteor file I use in this example. As I said before, in this example only we will use the checkbox No Classification. This checkbox overrides the classification values on the right side. We will need no topography, so we will jump to the Computation tab. By checking these buttons, the input files for the computation cores are written. GRAMM and GRAL are parallelized, so we will use 8 cores of this machine. After that we can start the computation. I select the computation core and the computation starts at this command window. After the first situation is finished, I will interrupt the computation by pressing the break button of the keyboard. Then I will force a refresh of that tab by changing to another tab and going back again. Now it's possible to evaluate the results using the mean concentration button and select the horizontal slice. To display the mean concentration of the first weather situation, I open the GIS window again and load the actual results using this tool. I select the concentration file, and as we see, the first dispersion situation was a western wind. It's possible to change the design of that contour lines. I do that in a simple way, so we have a basic setting for these results. Now I will close the GIS window and wait until the computation is finished. Well, the computation is finished now and it's possible to evaluate the mean concentrations again. I press the button Mean Concentrations at a height of 3 meters and open the GIS window again. The GIS window shows the updated results. Now it's possible to change the seasonal and diurnal emission rates of this source using this dialog. After that, you can check the annual emission rate using this button. Writing the new emission files and doing a new evaluation will write new result files that can be displayed in the GIS window. I hope you enjoyed that tutorial. Goodbye.